Before we start on this nice and wild journey into the complex numbers, I'm going to tell you a little story, which is a fictional story. However, it does not change the ideas and logics behind our number system. So, let's go back way before the year 0. And you are working somewhere in a store and you have some gold coins, and you are wondering how many gold coins you have. And you think and you think and you're like, I have some gold coins, but how many? At that point, we can say the natural numbers were created. Natural numbers, a set of numbers that we created to help us in our daily lives. It is denoted with an N with nice two bars on the left side, which contains whole numbers going from 0, 1, 2, 3, etc. up until infinity. The definition of natural numbers actually kind of depends on what book you're reading. Sometimes they refer to this as natural number set and with an asterisk on top of it with 0 included, but for now we do not care about that. Well, after that you have a store, which is nice, and you go to your friend's house and you are getting a little bit drunk on wine, and out of nowhere you break a vase. And your friend is like, oh, no worries, friend. I know that vase. It was 3 gold coins. And you're like, but I only have 1 gold coin on me right now. And he says, if you give me that one gold coin, and you give me 2 gold coins when you get back to your house, and you get the gold coins there, then I know you will pay me back eventually. And you're like, okay, great. So you give him 1 gold coin, and on your way home, you're thinking, well, how many gold coins do I have on me right now? I do not have 0, because if I have 0 gold coins, that means I do not have to pay anything to my friend again. So how many gold coins do I have? And you started thinking, and at that point, we had a problem. So let's add some extra numbers, calling the integers with a nice Z. And the integers are just the natural numbers, but also negative. So it is an addition to the set of natural numbers, which is called the integers. So this is called natural numbers, or natural numbers, and this is called our integers. Then you're happy, yay, another problem solved for us. And then you get home and your child is hungry, so you bake it a pizza, a nice round pizza. And your child is looking at you and says, if you bake 1 pizza and you cut it right now in 2 pieces, how much of the pizza do I get? And you're like, well, it's not 0 pizza because you have pizza, but it's also not 1 because you're not getting a whole pizza. So how much pizza do you actually get? Haha, introducing more numbers because we have a problem again. So we introduce some numbers, which are called the rational numbers. Rational numbers include all the previously mentioned numbers, so 0 as well, but also 1 divided by 2, 3 divided by 4, 6 divided by 9, but also its negative variant, minus 6 divided by 9, 6 divided by minus 9, minus 6 divided by minus 9, etc. All fractional numbers and numbers that were already in the integers are right now in the set of rational numbers. And you're thinking, yeah, this is everything we need. Then on the other side of the world, or maybe closer by, and you are one of Pythagoras' followers, Pythagoras with his nice theorem of a squared plus b squared is c squared. And you're his follower, and you're like, Pythagoras, my man, I actually have used your nice formula for a triangle, and I actually get to square root of 2. And I tried, but I could not write it as a fraction. And Pythagoras was like, okay, nice. And then he stabbed you, because when you said that some numbers could not be written as a fraction, they would literally stab you back in the days. So, shit's getting lit in the math world. But eventually they reconciled and were like, okay, we actually do need more numbers called the irrational numbers or the real numbers. And they consist of all the numbers before, all the fractional numbers, all the integers, all the natural numbers. But they have numbers that cannot be written as a fraction, like e, pi, square root of 2, square root of 5, etc. And now we come to another problem. We're like, if I take the square root of 9, it's 3. If I take the square root of 2, it's a decimal number. But however, if I take the square root of a negative number, it's impossible, because two numbers multiplied with each other can never be negative. Aha, do we say. Every time we had a problem so far, we just add a number to our already known set of numbers. So let's do that again, called the complex numbers. The complex numbers just consist of all the numbers before, only adding one, which is I. And it is defined I squared as minus 1. We never write down I as square root of minus 1 like this, because if you would write it down like this, you would run into problems. And while math is rigorous, the complex plane is actually defined a little bit different than how I'm stating it right here, but that's getting into the nitty-gritty details of math, and we do not want to do that for this video. So we have the complex plane, yay! You also might wonder, well, do we actually go on beyond this? Well, actually, yes, you could. You could actually go to the next letter, which is H, and then you could go to O and to S, and there are way, way more even behind this, but we do not care about those. Great. So we have the complex number system, the complex set. Well, what does it mean? Let's say we have a complex number. Let's call it number Z. Z is usually used for complex numbers. It has two components, A and B, I. That's how we write it. And both A and B are real numbers. So if we take an example, Z, let's take it as 3 plus 2i. And we also have another complex number called W, which we call C plus di. And with a nice example, let's take it as minus 2 plus I. These are two complex numbers where we have a real part and an imaginary part. So if we write it down in terms of mathematics, if you take the real part of a complex number, in this case it is 3. If we take the real part of W, in this case it is minus 2. If we take the imaginary part, it is called 2, not 2i. A lot of people make this mistake. It is without the I. And then the imaginary part of W is 1. It's 1 times I. Why numbers are written down like this will be made more clear when we talk about the complex plane in just a minute. First, we're going to talk about how we're going to add, subtract, and multiply these complex numbers. So, for addition, let's do the first one here. Addition. We get, very straightforward actually, A plus C. Let's go a little bit up so we see that. There we go. We get A plus C plus B plus D I. It is just as you would add two vectors actually. The real part plus the real part and the imaginary part plus the imaginary part. For our example, these two numbers here, let's write these in dark blue now. We get 3 minus 2, because plus minus will turn into minus, plus 2 plus 1i, which is 1 plus 3i. Now we get subtraction. subtraction, let's actually write down what we did here. We did here z plus w. Here we get z minus w, which is, well, almost the same. It is a minus c plus b minus di. And in our example, that results in 3 minus minus 2, which is plus 2, and 2 minus 1, I, which results in 5 plus I. And now we get multiplication of z times omega, z times w, apologies, and is actually the same as working out brackets. So assume that we actually have this multiplied with each other. You would multiply the 3 with the 2, the 3 with the 2, and the 3 with the I, then the 2i with the 2 minus 2, and the 2i with the I. And that's exactly how it works with this multiplication. However, if you ever stumble upon I times an I, in this case 2i times I, then you get I squared, and I squared is defined as minus 1, removing the imaginary number. So if we would write that down in terms of our complex numbers, we would get AC minus BD plus AD plus BC I. And for our example here, let's just write down 3 plus 2i minus 2 plus I. And we're just going to work out the brackets. That's actually all we have to do. So we get 3 times minus 2, which is minus 6. So we have 3 minus 2. Now we do 3 and I. So we get 3 times I is plus 3i. Then we get 2i times minus 2. And 2i minus multiplied with minus 2 will result in minus 4i. And then, of course, we have 2i times I, which results in 2i squared. But I squared is minus 1, so we get minus 2. And then we just can rewrite everything, which results in minus 8 minus I. So that is our two numbers multiplied with each other. Now, for these numbers, this form of a plus bi, we have written down here, is actually called the Cartesian form, which was named after René Descartes. The logicality of this comes from the complex plane, so I will talk about it right now. So let's assume we have a line here, and if I draw another line, you would instantly recall this as axis. I would normally write down as an x-axis and y-axis. However, right now we're not going to do that. What we are going to do is write this as our real part. So this is actually our real axis. And just write down as our real axis. On this axis is 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4, and minus 5. And right now we do not have a y-axis. We actually do have an imaginary axis. So let's call this x imaginary. And on this we have I, and then we have 2i and 3i. And this is the same as actually the axis system that you already have imprinted in your memory so many times in high school. Minus 4i, minus 5i, etc. So if we have our two complex numbers, which was z of 3 plus 2i, and w, which was minus 2 plus I, if we would denote them here, we would get 3 plus 2i. So 3 plus 2i would result in this point here. This is z. For omega, it's the same thing. We get minus 2 on the real axis. The real part is minus 2. Imaginary part is I. So we get here omega. Sorry, w. Now we have z and w here, which is good. Later, right now we have defined numbers with their real part and their imaginary part, the x and y axis, or the real and imaginary axis. Later you will see we can also define numbers as a vector. So you would get a distance from the origin and an angle phi, but that is called the polar form, which will be handled later in another video. For now we have these numbers. And of course, with the complex plane and complex numbers come some definitions. For example, we have our complex conjugate. So complex conjugate. What does it mean? A complex conjugate of a number, denoted with a bar or sometimes even a star, but I like to use bars, is actually the same thing. However, instead of a plus bi, we actually have minus. So we just flip around the imaginary axis. So for our example here, that would mean 3 minus 2i. So visually, that would be right here. This is the conjugate of z. And the same way, we have a conjugate of w, which is here. You can see that my axes are not really nicely proportionate. So the conjugate of w is minus 2 minus I. And the conjugates are very, very nice, because when we divide two numbers, we actually use a conjugate to get a very nice answer. So this is called the complex plane. Let's right now look at the division and why our complex conjugate is so important. So we have z divided by w, which is 3 plus 2i divided by minus 2 plus I. If you're ever dividing two numbers, it's always probably better to use a polar form, but if you cannot, if you are in Cartesian form, as you are learned right now, it is actually very good to multiply this always with 1. However, we are rewriting 1, because we can always multiply with 1. It doesn't change the outcome. But we're going to rewrite 1 as a fraction, 1 divided by 1. And these 1s we can also rewrite. Namely, we're going to multiply with the complex conjugate of the denominator. So we're going to multiply minus 2, and not plus I, but minus I, divided by minus 2 minus I. This is still 1, because the numerator is the same as the denominator. And this is the complex conjugate of the denominator, which is actually what we want. And why is that? Well, let's multiply the denominator and you'll see what we're talking about. So we get minus 2 multiplied with minus 2, which get us 4. And we get I multiplied with minus I, which is minus I squared, which is plus 1. Now if I do minus 2 multiplied with minus I, you would get 2i. But if I multiply I with minus 2, I would get minus 2i. And these would cancel each other out, which is very nice. We do not really like complex numbers or imaginary numbers in our denominator. We just want them removed. And it's easily done if you just take the complex conjugate of the denominator. So we've just done that. For the numerator in this case, we still have to do complex multiplication. So if we do that quickly, then we get to minus 6 minus 3i plus 4i, no, minus 4i plus 2 if we rewrite everything, then we get to minus 4 minus 7i divided by 5, which in turn, if we split up the fraction, we get minus 4 over 5 minus 7 over 5i. And this is again in Cartesian form, and this is also a question they sometimes ask in exercises or on the exam. And that is one way to surely remove the imaginary number or I from the denominator, because having an I in your denominator isn't really nice. Then one more last thing, because we are looking at the complex plane, I said that you have a Cartesian number right now. We can actually change it to a polar number. Well, this purple line right now, the distance from the origin, because we have our Cartesian number, is very easy to calculate, because we can actually just use Pythagoras theorem for this. There's like a 90-degree angle there. So if we want to know what the distance is, which is also called the modulus, so we had a complex conjugate. Right now we are talking about the modulus of a complex number, which is denoted by 2 bars around it, the modulus of z, which in our case is nothing more than Pythagoras theorem, so a squared plus b squared. And just taking the real part of z and the imaginary part of z and squaring them. Because if you look at the complex plane, the distance on the y-axis, or in the imaginary axis, this distance is 2. We denote everything with I, but the distance in itself is still 2, and the distance on the real axis is 3. The I is just, it's imaginary. We add it here because we have the complex plane, but its distance, its imaginary part, is still 2. That's why we define the imaginary part of a complex number to be without the imaginary number y. So if we do that for our number, for our z, then we would get, of course, 9 plus 4, because we get 3 squared plus 2 squared, which is square root of 13. If we do the same for w, we would get a 4 plus 1, which is equal to square root of 5. And this is what the modulus is of a complex number. And these are the biggest things of the complex plane, of the complex number system. And the complex plane will be seen much, much more in the course, and is very, very handy in solving some polynomial equations that normally could not be solved because your discriminant or your solutions did not exist in the real number set, but they actually have solutions in the complex plane. So the complex plane is very, very nice, and these are some ways in how to work with them.